Logistic models can be modeled with a recursive formula, and this formula looks crazy. I want to point out, though, that it's pretty similar to the exponential growth and decay model. We remember that for an exponential, I'll write this, I'll label it exponential. The recursive formula was Fn equals Fn minus 1 times 1 plus r. Notice that we have that Fn minus 1 and then 1 plus r. The only difference is that now r is being multiplied by this quantity here. Okay, I'm just going to point out this number k is that's our carrying capacity, or our limit to growth. Limit to growth / carrying capacity. Carrying capacity. Okay, for any logistic growth model, there's some limit to how much we can grow, and that's what this k is. So notice that if we've gotten really close to k, if the size of, say, a population is really close to k, then this fraction will be really close to 1. And if that's really close to 1, then 1 minus that will be really close to 0. So this formula tells us that if I'm close to that carrying capacity, if I'm close to that limit, then I'm not going to grow very much because I'm so close to my limit. So there's our formula for the for logistic growth recursive formula. Let's look at an example. Assume there's a certain population of fish in a pond whose growth is described by a logistic equation. It is estimated that the carrying capacity for the pond is 1,000 fish. That's K. I'm just going to go and write that out. Absent constraints, the population would grow by 140% per year. Okay, what that means is that we are going to get an extra 140%. So R is 1.4. Okay, that's the growth factor without constraints. We want to write our recursive formula modeling the number of fish. So we have our general recursive formula is Fn minus 1 times 1 plus r times 1 minus Fn minus 1 over k. That's our general form. And we already know r and k. We just plug those in, and that's our recursive formula. So Fn equals Fn minus 1 times 1 plus 1.4 times 1 minus Fn minus 1 over 1,000. That's all we can say. We don't know the initial amount, so this is as much as we can say about our recursive formula.